Hello everyone. So today for the learning lecture, I would like to present you about the flow networks and optimization techniques on flow algorithms. So let's look about the flow networks. What are the flow networks? So what is a flow network? A flow network is a directed graph with directed edges, and we have two distinguished vertices, that is S, the source, and T is the sink. And we have edges, and these edges are directed. So in this notation, like you see 3 over 5, so 3 is the flow in the direction given by the arrow. That means there's a flow of 3 from S to A, and 5 is the total flow in this edge. So that means there's a flow of 2 from A to S. So, and also these capacities should be non-negative. So such a graph is, we call it a flow network. So then let's see why we need these things. So think of a road system like this, a complicated one. So in such a system, we have to calculate what is the traffic condition and how many vehicles are there at this time. So is this enough? Is this roads enough? So in such situations, we need these kind of networks to check if these things are working well, and also for data network routing, and maybe in pipelines or drainage systems, we need to measure if these infrastructure is enough for holding these waterways, and also for supply chains to transport goods and people. So that is why we need these flow networks in real world. And let's move on to the problem, the maximum flow problem. So in this problem, so the goal of this problem is maximize the flow from the source node S to the sink node T, while respecting the capacities on the edges. That means uh, we need to calculate the maximum flow from the source to the sink. So we are given a list of edges, and we need to find out the maximum. So why we need to solve this problem? Because in most cases in real world applications, we need this one because we need the maximum movement of goods in transportation and logistics. We might need the optimized data flow through a network of systems, or a maximum bipartite matching to assign workers to a task. So in such situations, we need the maximum flow, the maximum matching we can obtain through such a graph. Now let's look into the flow algorithms and optimization techniques we can use on these algorithms. So under this topic, I would like to talk about main three algorithms, and several techniques we can use to optimize and like improve these algorithms when it comes to the real world applications. So first of all, in almost all the algorithms, we need these two concepts, the residual graphs and augmenting paths. So in a residual graph, a residual graph is a graph that represents the available flow for each edge. That means, like as I told you, there's a capacity in each edge, a flow. So a residual graph is what it is represented through. So this is a residual graph, you can see. So these values represent the flow in bidirectional way, and an augmenting path is an available flow path from the source to sink. So in this example, you can see the purple color path is an augmenting path. So you can start from S, and you have a path from S to T, and the bottleneck value of the flow is 3. So you can see, like in the first one, we have remaining flow of 4, but in the second one, we have only 3. Even in the second one, the third one, it's 3, but in the last one, we have 5. So the bottleneck value for this path is 3. So we have an augmenting path with the flow of 3. So then let's move on to the our first algorithm. So this is most simple algorithm we can use to find the maximum flow. So you can see this is the residual graph we are having. So what we first do is we start with an initial flow of 0, and then we need to find the augmenting paths from source to sink. And I think some of you might familiar with BFS and EFS. BFS stands for breadth first search and EFS for depth first search. So with these two, you can use either, and with these two algorithm graph traversal methods, we need to find augmenting paths and increase the flow at each time. So we are going to run DFS in this graph and update the residual capacities. When updating the residual capacities, so you can see in the first picture, there's a yellow color path, and the bottleneck value of that path is 2, because the second value is 2, the maximum value. So we are going to have a flow from source to sink equal to 2, and when we are updating the values in the second one, you can see the first the middle edge got 0 flow from 2 to 4, and it gets updated from the in the backward direction. That means, like, when we are reducing the flow from 2 to 4, we are increasing the flow from 4 to 2. We need this because let's say, so we might choose not an optimal path. So that's why we need to update this residual graph in the backward direction. And with such updates, we can continue the process, and we repeat until we have no more augmenting paths. So the time complexity would be, so for one BFS or DFS, we have a time complexity of big O of E, that means the number of edges. And in the worst case, we have to run this algorithm for the for time equals to maximum flow. That means, like, imagine a graph with a capacity of each edge is 1. So the maximum flow would be the so for each increment in the maximum flow, we have to run a DFS. So for each DFS, the time complexity would be E, and E times maximum flow would be the time complexity. Now the problem is this maximum flow can be really big, and the edges can be also really big. We need an efficient algorithm for the Ford-Fulkerson algorithm to find the maximum flow. So that's when we get this optimization, BFS layer graph optimization. So here we are doing something really intuitive, but that makes a huge difference in the time complexity. So what we are doing is, first we run a BFS from the source to sink. In a BFS, you can create a level graph. Level graph means we are just calculating the distance for each node from the source. So here, the distance from the source is 0. I have shown in brown color. And the distance from the source to the first node is 1. And for the second one is it's also 1. And for the third node, it's 2. And fourth, it's also 2. And for the fifth node or the sink, the level of that node is 3. So that means the minimum distance is 3. So after we have created this layer graph, we are not going, when we are finding augmenting paths, the rule is we have to always go to a level, a node with a higher level. That means, like, you cannot go from 1 to 1 or 1 to anything less than 1. That means, so let's say you are at the node 3 and you cannot go to the node 4, because they have the same level. So it always has to go to a node with a higher level. So In the second step, in the second picture, you can see we have updated uh, the maximum flow and the residual graph. And in the second run, you have only two edges, because usable edges, because uh, sorry. Um, so in the second picture, you can see the third node is not accessible from zero. So the maximum flow is achieved even from the first picture. Um, and we have to repeat the DFS until, so as I told you before, after we have created the layer graph, then we run DFS to check if the sink is reachable. And when at each time we find an augmenting path, we update the maximum flow. And we repeat this DFS until we have a blocking flow. Blocking flow means a situation where you cannot uh, access the sink from the source in that layer graph. That means like you have to respect those levels, and also sometimes like you might be able to access the sink without respecting those levels, but you have respecting those even after respecting those levels, you cannot go to the sink. So then we have to update the level graph again. So that is in the second picture. In this one, the time complexity is reduced to E times V squared. So this how this came. E times V squared came. So as I told you, at each time we have to run a BFS, right? And in a BFS, it is big of E, and the lemma one is uh, the level of a single node. Let's say there's a node called V, and the level of V is not going to decrease in an iteration. So in the first phase, let's say the level of the uh, first node is 1, and in the next one it's not going to be decreased. It can be the same, but it's not going to be decreased. So with that one, so that's the first lemma. And in the second one, we can prove that the sink's level is always increasing, not even the same, um, because if there's a same level for the sink, then we haven't reached a blocking flow in the previous one. That means we could have come to the sink with the same level. So that's a contradiction. So definitely the level of the sink is going to be increased by 1. That means, and also the level of the sink cannot exceed the number of vertices in the total graph. So that is V, and V times, and in one phase we might have to run DFS for V times. So in one phase, the time complexity would be E times V, and for all the phases, it can be E times V squared. So that's how we get this time complexity. And there's a special case for bipartite matching. That means you have two sets and you have to match those two sets. So in such cases, we have a time complexity of E times square root of V, and this is really good complexity. But the problem is the implementation is hard for a bipartite matching, because we have much more easier implementations for bipartite matching. So that's when we have Hopcroft-Karp algorithm. So this is specifically used for bipartite matching, and this might be much easier algorithm. So let's say we have a set of a list of names, and for each of these students, there are several numbers we can match. So for Billy, it's 1 and 4, for Emily, 7, 3, 6, and so on and so forth. So in the second picture, you can see there's an initial matching. So let's say we can match Billy to 1 and Emily to 7 and like that. But we have Luke and Raj without any match. So for Luke, it's only 7 and 2, but both of them are already occupied by Emily and John, and the same for the Raj. So in such cases, we are going to increase the maximum flow or the maximum matching without making the already matched nodes unmatched. So basically what we are doing is we get the unmatched node from the left side. So that is L and R in the third picture. And then we create the graph. Um, so for L, the two remaining edges to which he can be connected is 2 and 7. For R, it's 7 and 6. For a right side edge, we have to connect it to the one it is connected. So when it comes to 2, it should be J, because J is the one we have already matched. And for J, we have 4 and 5 remaining because we have already connected J to 2. So we have 4 and 5. So likewise, we are going to create this graph. And when we find, we have started from an unmatched node from left side. When we are creating this graph, at a point, if we find a node which is unmatched from the right side, we have a match. So how we match? So right now we have matched J to 2. So what we are going to do is we connect L to 2 and remove this matching from 2 to J, and we'll connect J to 4. So J to 4 is a legal one, I mean like a valid one. So John has 4 and Luke has 2. So we increase the flow without making John unmatched. And also we have a matching for Luke as well. So likewise, we are going, if we find an augmenting path like this, uh, at point we find a unmatched edge node from the right side, we have an augmenting path and we backtrack through this path and we have a higher matching like this. So even in this one, the time complexity would be E times square root of V, and the advantage of this rather than the DNX is this is easier to implement rather than the DNX algorithm, because in DNX we have to run a BFS each time and DFS inside it, so it will be harder to implement. But in this one, it's much easier. So yeah. Now we can move on to the some optimization techniques. So this is the we call scaling techniques, and this is prioritizing edges with higher flow capacity. So this is just a greedy technique we use to optimize the maximum flow. I mean the time complexity. Uh, because when we always choose edges with higher flow, there's a higher probability to get a maximum flow with a less time. So what we do is first we set the value delta or the scaling factor equal to the maximum capacity of the given graph. So in this example, it's 14. And then we only use the edges which is equal to, which is greater than or equal to that scaling factor. So in this one, it's only 14. So let's consider a graph with the same with the same capacity, and it has several edges with the same capacity. That means the maximum capacity. So you might find an augmenting path. But if we cannot find a path, what we do is we are going to replace or the update the scaling factor by the power of 2, which is greater than which is the greatest power and of 2, and which is less than the previous delta. So in this example, when we start from 14 and we try to find augmenting paths, and after that we reduce it up to 8 and then into 4 and then into 2 and so with this technique there's a possibility to have a higher maximum matching. There's a higher possibility to obtain maximum matching in a lesser time, and also like even without a scaling technique, you can always pick up the higher edge at each node. So and we can use a data structure like priority queue. So priority queue is a binary data structure. So the time complexity of updating or removing a value is log n, so it's not going to be a problem. So you can use that one as well. If you are using a binary, it will be easier uh, to achieve the maximum flow in a less time. And these are some heuristic optimization techniques we can use to optimize the algorithm. So, as I told you, creating a layer graph to optimize the augmenting path finding. So, we have seen that in the Dinix algorithm, how the time complexity is improved from the Ford Fulkerson to Dinix algorithm. And in bipartite meshing, a greedy meshing on initial graph can optimize. So if we go to the subgraph graphs algorithm, so we can just pick some values and connect them randomly in a greedy method. So first we go to Billy and we connect it to 1 without thinking anything. Like if 1 is available, we connect it to Billy. And we go to Emily, the first one is 7, we connect to 7. And John, it's 2. So likewise, we can have a initial greedy matching and then start updating the value. So that can improve the time complexity because it cannot increase the worst case time complexity, but in average case, it can make a huge impact. So that's about the greedy matching on an initial graph. And also the highest label variant of push reliable algorithms. This is the most efficient algorithm we already have. So in Dinix algorithm, it's e times v squared, but this one it's v squared times square root of v. So this is a really good algorithm, but the implementation is hard. But if we need to use it, so this is the best time complexity we have achieved so far. And so the next two are like literally heuristic techniques which we can use. So when we are choosing edges or finding augmenting paths using a BFS or DFS, we can consider the current bottleneck. So if we have a current bottleneck of 2, there's no need of choosing for a higher value. So always you can, because the bottleneck is 2 now, so it's enough to go for 2. And if it is getting low, we can move on to that one, but otherwise we can go for a higher value. And also if we have a really large graph, in real world applications we have such graphs. So in such cases, if we can estimate the maximum flow and terminate if the current value reach almost the maximum flow. So that means if we can estimate the maximum flow, and then if we have achieved the current flow to be almost the maximum flow, we can terminate the program and make some 3D approaches to optimize the matching. So we have pros and cons in using heuristic techniques to optimize an algorithm. So what are the advantages? So efficiency is increased because that's the main goal of this, because the problem is in real world applications we don't have such a huge computing power to process all these things. So using heuristic techniques, we can have better approximations, because most cases we don't need the exact optimum value. We just need to have a better value. So if we can achieve a better value, that would be great. And simplicity, because most of these greedy techniques are easy to implement rather than having complex algorithms. And it will always, most of the times it will give good approximations. So the disadvantages are we cannot have the exact value. The best optimal value we cannot achieve. We have only a local optimas, and sometimes uh, we cannot guarantee the best solution. In such cases, we might have to go for something else, but the end of the day you can't get the optimal value, and sometimes in greedy algorithms we can get stuck in local optima. So when we find a local optima, it's not getting increased or improved beyond that one. So in such cases we have some cons in using heuristic techniques. So yeah, that's about the disadvantages of the heuristic techniques. And so yeah, that's the end of the presentation. Thank you, everyone.